So here's the story on stability, best case, average case, and worst case for all of the algorithms that we considered. And so we see that insertion sort, bubble sort, merge sort, counting sort, and radix sort are all stable. And selection, shell, heap, and quick sort are not. We see that out of the n squared, out of the top three, which are n squared, order n squared sorting algorithms, only insertion sort gives us improved performance in the best case. Its average case requires that we move sort of half of the values around, and so on average, that will be an n squared order algorithm. So everything else is n squared as far as the n squared algorithm goes. So for shell sort, we basically said this is roughly n to the 1.5 is the average case. If the data is already sorted, then it's n log n, but that's in the best case only. So roughly n to the 1.4, n to the 1.5 is the average case, and it can go as bad as n squared. Heap sort is n log n in all cases. Merge sort is n log n in all cases. Quick sort is n log n in the best case. But as we pointed out, if we pick the worst pivot that we can possibly pick at each step, we will end up with an n squared algorithm. So basically the average case is going to be between n log n and order n squared. For counting sort, it is linear in terms of the maximum value in the table plus the number of bins or buckets that we place the values in, and that is regardless of whether it's the best, average, or worst case. And finally, for radix sort, we're big O of the number of passes and the number of buckets, and n, of course, which is the number of data items that we're putting in. So p times n plus b is still linear with respect to n. We're just giving n a coefficient, the coefficient of p, which is fixed for the number of passes. Therefore, this is a linear sorting algorithm. So this is the result of some empirical studies done on sorting routines for going from all the way from 10 items all the way up to 1 million items. And the key here is to just show how the n squared algorithms really suffer as we start increasing the number of data items. And then we've got some /O's on the side here. So we have a shell, /O, merge, quick, and heap. Those optimizations are listed to the left. So by shell optimize, we mean that the divisions of sorting are by 3, so that we would probably do, say, a 9 sort and then go down to a 3 sort. So for merge sort, the insertion sort kicks in whenever the sublists are less than length 9, and that's the optimization that was made. So in other words, once we get a sublist to be less than size 9, rather than continuing to assemble per the merge sort algorithm, we just simply invoke insertion sort in this optimized method, and you see that there is a little bit of a gain as we go from somewhere around 197 to 219, and we don't know what the units of time are here. You see that the shell, I did not point out the shell increase in performance, but there is a little bit. Finally, for quick sort, once again, once the lists get below size 9 if we do an insertion sort at that point. That gives us a slightly improved performance. And with respect to heap sort, if we use an array rather than a class, you'll recall from homework 5 that using just a raw array is going to be much faster than using something like a vector that has overhead. And so if we do that, then we're able to get improved performance, and that's what we mean by heap optimized. And we see those values here. Finally, there are two values for radix sort, but these use bits, and they're not exactly like the ones that we demonstrated in class, so we won't consider those. The other key thing to remember here is that even though quicksort can be of order n squared, it's actually a very efficient algorithm, and most of the time if you pick good pivots, and there are lots of methods to pick pivots as I mentioned, you will get excellent performance. So you can see that the quicksort methods for sorting 1 million items provided the least amount of time, i.e. the best performance out of any of the other sorting algorithms. So with that is the sorting block. And we've taken a look at a number of sorting algorithms. We looked at insertion, bubble, and selection sort as n squared algorithms. And then we looked at shell sort, which is in a class by itself. And then heap sort, merge sort, and quick sort, all of which can give us order n log n behavior. And finally, we looked also at radix sort and counting sort, all of which are special case sorting algorithms that give us linear time behavior. That concludes the sorting block.